Okay, so you remember that we are doing this balancing. Okay, we are doing balancing for the rotary shafts or component, and there are how many types of balancing?
So static and dynamics.
Static and dynamics. Okay, so we have done this static balancing. Now we are going to do the dynamic balancing. In the static balancing, all the masses are in the same plane. Okay, and then there is a problem. The problem is that we have inertial axis and we have a rotational axis, and they both are just move apart parallel. In dynamic balancing, they move apart not parallel, but in the form of the angle. Why did this happen? Because we have a masses in multiple planes. Okay, for example, compression. Okay, circular compression or gas turbine. So you have different stages. So on the same shaft, you have multiple stages, and when you have multiple stages, there is a possibility that when they are unbalanced, and then the forces are on the line. So what it can produce is it can create a moment effect. So when the masses are in multiple planes, and let's say some planes are not balanced statistically, the force will create, and the force what will do along with it, it will create couple. Okay. So in case of the static balancing, we have to balance only the masses, but while in case of the dynamic balancing, we do not only need to balance the static masses, but also this couple. So what will happen? In addition to some more equations will come up. So I give you the printout. Can you have a look at those printouts? Equation 14.5 and also this equation figure 14.6. So you can see that over here we have multiple masses. Okay, you can see the multiple masses in different planes. So let's say this one is 0.0, this one is 0.Q. This is your plane 1, plane 2, plane 3, and then plane 4. So 3 different planes, and the masses distribution are in each plane. The masses are M1, M2, M3. At a radial distance of R1, R2, R3, and at the angular distance of theta 1, theta 2, theta 3. So what will happen over here? Since we have to balance it, balance the couple or couple moment, so the couple moment needs another plane out of that plane to balance the force. So we have C1 and C2. So we are going to put our countermass at C1 or countermass at C2 to balance out this additional problem we have. Okay, C1, all the distances are measured from this, so let's call it reference plane, RP. So what we are going to do, we are going to measure. So before that we have only 3 parameters, theta, r and m, mass, angular position and radial distance. Now this time we have another addition over here, which is the length, because we are going to, what is the moment is force multiplied by the distance. The distance will come, all the distance will be measured from this reference plane. Okay, in that case, we have this equation 14.5. So you can see M1, I give you the printout, you can look at it. M1 R1 omega square, M2 R2 omega square, and 3 R3 omega square. If everything is balanced, we do not need to worry about it. And also for the couple moment, this is the equation M R omega is a force unit. We did the dimensional analysis last time, and it was equivalent to the force unit. Now multiply the force with the length. So you got another equation which is on the other side of the page, 14.6 is M1 R1 L1 omega square, M2 R2 L2 omega square, M3 R3 E omega square. All the subscript 1, 2, 3 are in different planes. Okay. And omega, there is no subscript because it's on the same chart. Whatever is the plane you're talking about, they are all on the same angular velocity, omega. Okay, these are the two equations when you do not have any problem, when everything is balanced. So the summation of the forces and summation of the couple or moment is equal to 0. What will happen if they are not equal to 0? So in that case, for the equations, we need to change those equations. Okay. So we need to add in this equation 14. We need to add more masses at different locations. Okay. So equation 14.5, which is just the force equation. Okay. So if unbalanced, so what we need to do, we need to add one at the C1 and one at the C2. Okay. So what we'll do is MC1 RC1 omega square plus MC2 RC2 omega square. So based on this forces, which is equation 14.7 in your printout, you can see it over here, it will be balanced. And then if you remove the omega, so all you get is M1 R1, M2 R2, M3 R3, MC1 RC1, MC2 RC2 equal to 0. Okay. So in general, what we can write is this equation. Summation of MR plus MC1 RC1 plus MC2 RC2. Okay. On the other hand, now we are going to talk about equation 14.6, which is related to the couple. Okay, force multiplied by distance. So in that case, you can see this equation 14.9. So what happened in the 14.9 equation 14? We stand on this reference plane. So what is the value of couple on this reference plane? It's 0. Why it is 0? Because we need force multiplied by distance. If we take the C1 as a reference plane, the distance is 0. So the rest of the equation. So you can see in this equation 14.9, only MC2 RC2. So this reference, because we are measuring from here to here, so only the C2 will remain. Based on this, when we remove the omega, it will become 14.9a, and then you can see this equation will be shortened to summation of M L. Okay, so this L will appear over here. MC2 RC2 MC2 equals to. So unlike the static balancing, where we have only this term, now we have two separate planes, two separate masses, and then more equations. So each equation, let's say this is equation. Okay, I'll put the same number so that it will be 14.8, and this is equation 14.10. So what we are going to do now, we need to make these both balanced so that this will be in the dynamic balancing. We split this equation 14.10. Okay. And we can do the same component. Here M1 R1 L1 cosine, M2 R2 cosine, theta 2, M3 R3 L3 cosine theta 3, and so on. When we do the component of it, we get all the component, and once we get all the component, we add them together and then square and add them together. Once we do this thing, we ended up with this equation. And exactly the same way we dealt with the static balance. And then we have this tendency to minus MR and sin theta. So it's a summation sign, number of planes, we just keep adding all the number of planes, whatever the number of planes we have. So once we calculate, so now you can see we can find out, we have two equations. We can find out two variables, either the mass, either the radial location, or either the length, depending upon the input data. And then we can find out angular position. Once we are able to find out, so in this dynamic case, we need to find out the MC2 or RC2, LC2 or theta C2 first, and then go to the mass number 1. So using equation 14.8, we do the same treatment as we are doing it before, and we got this C1 RC1 equal to you can see there are two terms. You go there, it will become square. Cosine theta C2 square plus and then we have tangent theta C1 this term divided by this term. Okay. So now you can see that there are like so many equations and so many variables, but the procedure is exactly the same, a little bit more laborious, you can say, but the treatment is almost the same. All right. Let's start solving the first example. Okay, so I gave you the printout, and we are going to this is example number 14.3. Okay, got it? A rotating shaft carries 3 unbalanced masses. 4 kilograms. So what we'll do is do it again exactly the same way. We're going to make the table. Okay. So we need to have a table. Then we have a mass, then we have a radius, variable and units. Then we have MR, MRL. And then it's up to you if you want to use the theta term over here, you can use the theta term over here. If you want to use the theta term later on, you can use the theta term later on. Okay? Alright, so we have mass 1, 2, and 3, and then we have countermass 1, countermass 2. Alright, the shaft is rotating, carries 3 unbalanced masses of 4 kilograms, 3 kilogram, 2.5 kilogram, at a radial distance of 75, 85, and 50, angular position of 45 degrees, 135, okay? Now, the most important thing over here is that we need to find out these lengths. The second and the third masses are in the plane at 200 and 375 from the plane of the first mass. So sometimes I give you the drawing and sometimes I will not give you the drawing. So you need to extract this data from the input data over here. So you can see over here at the moment, the values are something like this. This whole altogether is how much? 800. This is basically bearing. And this is also bearing. So you can see the first mass and the bearing, the distance is how much? 75. From the bearing to the first mass is how much? 225. Between the second mass, between the first mass and the second mass, the distance is how much? 160. Okay, between the second mass and the third mass, the distance is
375.
And then here also the bearing, the distance is. Alright, before we go to this, we need to find out the length. Okay, what is L1? L1 is the length between the reference plane and the first plane. This is the L1. What is L2?
From the reference to this.
Reference plane to the second plane. Yes, you're right. And what is L3?
From the reference.
Everything will measure it, and similarly, LC2 is also from this. So what is the value of L1?
150.
So 225 minus 75, how much you get?
150.
225 minus 75, 150. What is the value of L2?
350. 350.
225 plus 200 minus 75. So you get this value of 350. What is L3? 375 plus 225 minus 75. How much you get?
725. 725.
Really?
500.
And what is the value of LC2? LC2 is from the reference plane to the LC2. What is the value of LC2?
600.
So the total is how much? 800? That is 800 is from bearing to bearing. Bearing to So 800 minus 75 from this side and 75 from the other side. So how much you will get?
125.
650.
125 or 625.
Oh, and you need to subtract it also. What is the value of C1?
0.
0, because
No,
it's a reference plane. We are measuring everything from it, so the length will not be considered for it, or 0 on the other. Okay, then we can have an R and an L. So we can write the values of MR, for example, in this case 300, 255, 125, and MRL is 2500, 89, 250, 65. So I'll put the solution. The solution is already with you in the few scan pages in the lecture notes, and I will put it separately if you want. So now what we need to do? Which equation we'll use first? This is equation 3.1. 2. Three. Okay, going back to the numerical. So they give some information. The angular positions are measured counterclockwise from the reference along the line x-axis and viewing the shaft from the first mass end. So if you look at the shaft from the first mass end, you will see like this. All the derivation we did it with the same assumption. So there is nothing new over here. The length is 800 between bearing, and the distance between the first plane mass and the bearing at the end is 225. So all these information are mentioned in the text form or in the drawing form. Determine the amount of the counter mass in plane at 75 from the bearing for the complete balance of the shaft. The moment you see that there are two planes, there are multiple planes, it is a dynamic problem. Okay, don't raise your hand in the assessment and ask me if it is a static problem of the dynamic problem. There is no word of dynamic imbalance or dynamic balancing is mentioned in this numerical explicitly, but you know this is a dynamic balancing problem. So we need to find out the counter masses and 75 from the bearing for the complete balance of the shaft. And then the rest of the information, the first counter mass is to be placed between the first mass and the bearing at the radial distance of 75. So we have this another 75 over here. And the second mass is between the third mass and the bearing at end of the radial distance of 40. Okay. So we need to find out the mass, and we need to find out the angular phase method. Okay? So which equation will you use first? Always in the dynamic, because in this equation, they need this MC2 as well. Okay? You need to see the data. In this particular example, we don't know the value of MC2 as well. So this equation will become two unknown, MC1, MC2. Cannot solve this equation. So we need to go on to 14.11, which is balancing through coupling. Okay. So we'll be able to find out. So in this equation, do we know the value of RC2? RC2. This is C2, this is R. So this is RC2. So we know this value. LC2.
Yes, good.
LC2, this is the value. We already calculated. Summation of, so this means M1, R1, M1, M2, R2, L2, M3, R3, L3. All these 9 values. Do we know this? All these 9 values?
Yes.
Yeah, here all these 9 values. And then there are corresponding thetas as well. So all these 12 values we know. And same with the sign relationship. Once you put all the values in it, you will be able to find out the value of MC2.
Doctor, we don't need MR for C1 and C2 for the first step.
No, because for this equation, this is a couple balancing equation. For this equation, we put everything on the C1. Okay, so all these C1 gone. So
I mean for MR, summation MR, it should not contain C1 and C2 values of MR.
So only we need these 3 values, this, and this. Okay, not for the countermasses. Okay, when you solve this equation 14 point this, you will be able to get this MC2 and the equation 2.86. Now you know this term. In this term, there is no countermass. Okay. If you look at the derivation which I showed it to you on the printout, you see that there is no countermass because the countermass. Because if this term is equal to 0, it means these all are balanced. If they are not balanced, that's why we introduce this counter couple standing at the point C1, which is our reference plane RP. Understand? Make sense? So now in this equation, only we need to find out MC2, and then now we know that this part and this part. So we know this value, we know this value. Cosine theta C, and we discussed that the problem with the tangent that is always written within that quadrant. So what the value will got it is 329. Okay. Once we are able to find it out, so step-by-step calculation you need to do it after the class. Okay. You need to put all the values into it. It's up to you. If you want to put the cosine over here, or if you want to expand the table with the cosine and sine relationship. Now in this equation, MC1, we have to calculate, we have to find it out MC1. Do we know the value of RC1?
Yes. No, 0.
Yeah, it's there. RC1.
75.
It's given. MR, cosine. So M1, R1, cosine 1, M1, R, M2, R2, cosine 2, M3, R3, so all these 9 values plus in the previous step we calculate this MC2, RC2 is given, theta C2 we calculated in the previous step. So we know this value from the previous step. This one was given. We know this value from the previous step. MR, we know. Similarly for the sine, similarly for the M, R is given and theta we calculated from the previous step. So in this equation, only one unknown. All you need is to put all the unknowns in there and you will be able to find out. MC1 and the value of MC1 over here is once you do this thing, you know the value of this part and you know the value of this part. You put it here, 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 cosine, and hopefully we will be able to find out C1 and the value of the theta C1 is so it's exactly the same way we solved it. The static problem, the only additional thing over here is that the couple will come over here and then we need to. Understandable? Can you do it? Can you all do it today? And send it back?